This video is on heat as it relates to reaction energy. So thermochemistry is the section of chemistry that deals with heat. And again, heat is a form of energy. So that is part of the reason we're interested in chemistry, is the energy that we can get from types of chemical reactions. First thing we have to do is make that distinction between heat and temperature. We know from our previous studies that temperature is the average kinetic energy of the particles. It's how fast or how much energy, motion energy, do these particles have on average. Heat is a form of energy, and that is going to be the total sum of the kinetic energy of the particles. So how much energy is being given to these particles to make them move faster, which would increase our temperature as we add heat. Heat is always going to flow from matter at a higher temperature to matter at a lower temperature. So if you're holding a nice icy glass of water, it's going to feel cold, not because that glass is radiating cold. It's going to feel cold because you're the matter at higher temperature. Your hand is going to be a higher temperature than that glass of water, and heat will be leaving your hand and moving to the glass. And that removal of heat from your hand is what gives you the feeling of something being cold. So there is no such thing as radiating cold. It's just the removal or addition of heat that gives us the feelings of hot and cold. Now, heat is going to be measured in joules. That's what we're going to deal with here in this class. Heat is, as far as English units or imperial units, heat is measured in calories. Now, that's the same calorie that would be in, like, on your cereal box. If you, let's say your cereal is 200 calories, that is how much heat or energy you have to expend to burn off that amount of food. Now, technically what's on your food is a kilocalorie, where they tried to take these imperial units and apply the metric system to them, and it's just a big mess. We will just stick with joules, which is the SI unit or metric unit for heat. Now, heat is a Newton meter. A Newton is a kilogram meter per second squared. So a Newton meter is a kilogram meter squared per second squared. Sometimes it's nice to know how the units break down, but that kind of got hard to say. And so they said, let's just call this a joule and be done with it. But that's how you break down a joule. Okay, so this is a little bit of review talking about heat and phase changes. We've looked at these heating and cooling curves so that we could determine, when we talked about states of matter, so that we could determine when a substance had its melting point and boiling point. And we also discovered during that time that we could also figure out the state of matter something was in based on where it was on the heating and cooling curve, or where a particular point was, and that when we went through a phase change, the temperature did not increase. So when we're talking about phase changes, we're talking about these parts right here, where even though we're adding heat, our temperature is not going up. And the reason for that is that the heat that's being added is going into breaking intermolecular forces to separate those molecules from one another. And that does take energy. So that has to be part of our calculations when we talk about heat, that it does take energy to go through a phase change. Now, remember that energy is required to go through a phase change, and this is called latent heat. So on a graph, I say that the latent heat is the part laying down. It is the heat required to go through a phase change. And again, the heat that is being used during a phase change is going into breaking intermolecular forces, not bonds, and separating those molecules so that we can go from like liquid water to steam. We have to break those hydrogen bonds in there. Now, you'll notice that the length of this part right here for melting is much shorter than the length here for evaporation. That is because it takes, when you're going from a solid to a liquid, you're only breaking some of those attractive forces. And then when you're going from a liquid to a vapor, you have to break the rest of the attractive forces. And this one is for water, so we are breaking those hydrogen bonds, the strongest intermolecular force. So when we are going through a phase change, we need to include the heat of fusion and heat of vaporization. What we're going to deal with are the ones for water because that's what's given to us in our reference tables. But we could apply it to any substance as long as we had the values of these. And the values of heat of fusion and heat of vaporization come from the amount of attractive forces that a substance has. All right, so what I have here at the bottom is a copy of the reference tables. This is on the front of your reference tables. And we have the heat of fusion of water and the heat of vaporization of water and their values and symbols. So if we're trying to calculate the heat, which is represented by Q, and I know that's weird, there isn't a Q in heat. The way we kind of get around that is that it's the quantity of heat, but just go ahead and associate Q with heat. It is needed to melt or freeze a substance, multiply the mass of that substance by its heat of fusion. So melting and freezing, you have to use heat of fusion. Now, this equation is given to you on your reference tables. Q is the amount of heat, and that's going to be measured in joules. M is mass, and it needs to be measured in grams. And HF is your heat of fusion. And again, you're specifically going to use this when we're melting or freezing something. All right, so how much heat is required to melt 10 grams of ice at 10 degrees C, at 0 degrees C. These equations only work at a substance's melting point or freezing point. So Q equals MHF. And so we're trying to figure out how much heat, and that is Q. Our mass here is 10 grams. And our heat of fusion for water is this 334 joules per gram. Gram cancels out. All we're left with are joules, and that is appropriate for heat. And this would be 334 joules. Now, a joule is pretty small. So a lot of times what we're going to see is if the heat is over 1,000, we're going to go ahead and convert that to kilojoules. So we just need to move the decimal over 3 places. So that would be 1, 2, 3. So 3.34 kilojoules of heat would be my answer. Again, melting or freezing, you've got to use heat of fusion. This is the amount of heat it takes to melt 10 grams of ice, that you have to add to melt 10 grams of ice. This is the amount of heat that would be released when 10 grams of water freezes. So that's how they work in the opposite phase changes. All right, so next, to calculate the amount of heat needed to vaporize or condense a substance, you're going to multiply the mass by the substance's heat of vaporization. All right, so for vaporizing or condensing, you're going to be using heat of vaporization, HV. So the equation looks very, very similar. Q is equal to M times HV. So our heat is equal to our mass times our heat of vaporization. So if I have this problem, how much heat is required to vaporize 10 grams of water at 100 degrees C? Again, this equation is only valid at a substance's boiling point, and for water, the boiling point is 100 degrees C. So Q equals MHV. And I'm looking for Q, so because I'm looking for heat, and the mass is 10 grams again, times my heat of vaporization, because I am vaporizing this substance. And we'll use that. It's at the bottom of the slide there from the reference tables. Grams cancel out, and so I'm left with 22600 joules of heat. Again, this is over 1,000, so we'll go ahead and convert it to kilojoules. 1, 2, 3, and so that's going to be 22.6 kilojoules of heat. This is the amount of heat we need to add to vaporize 10 grams of water. And that's quite a bit, again, because water has those strong intermolecular forces of attraction of hydrogen bonding. This would also be the amount of heat that would be released as 10 grams of steam condensed into liquid water at 100 degrees C. All right. Now, that works for our phase changes. The part you have to remember, and let me get back to that. The part you have to remember is which one to use, HV or HF. So you use HF if it's melting or freezing. You're going to use HV if you're vaporizing or condensing. And the equations are given to you on your reference tables, and so are these constants right here for water. Okay, so that's going through a phase change. But what if we're at one of those points where we're having a temperature change? How can we calculate the heat involved in raising the temperature a certain amount? Well, that has to deal with a substance's heat capacity or specific heat. The amount of heat transferred during a temperature change depends on three things. The first one is the nature of the material changing temperature. So I can be quite lazy when I bake cookies. And oftentimes I don't want to wash the baking sheet, so I'll put aluminum foil down. And then I have found that when the cookies are done, I can reach my bare hands into the oven and grab the aluminum foil and take them out of the oven without burning myself. But that's only if I just grab the aluminum foil. If I tried to grab the baking pan, I'm going to end up with blisters and some pretty severe burns. Well, what's the difference between the aluminum foil and the baking sheet? Well, one difference is they're different materials. Aluminum foil doesn't have as great a capacity for holding a heat as maybe the stuff that my baking sheet does. Another very obvious difference would be the mass of those materials. Aluminum foil is very, very light, so there isn't a lot of mass there. The baking sheet, though, is much heavier and so has a lot more mass in there. And the other one in this scenario would be the same, but for other materials, it's the size of the temperature change. How much is it changing temperature? So different materials have different capacities for absorbing heat. And this is what we call a specific heat. It is the heat that a specific substance can hold on to or absorb. So this varies for lots of different things. And you have your reference tables, which has the specific heat of a lot of different things. And we can use it for identifications, much like we did when we were calculating density. If we found a density of this, we could say, oh, it's aluminum, or okay, my density is 7.86, so this material must be iron. So we have the specific heat for a lot of different substances, including water in its various forms up here. Well, what is specific heat? The units kind of tell you what specific heat is. And I'm just going to take this first one right here. Joules is the amount of heat. So specific heat is the amount of heat it takes to raise 1 gram 1 degree C. So it's different for every substance. Water has a very high specific heat. It's like 4.18. While other substances like mercury has a specific heat of 0.14. It doesn't take a lot of heat to raise 1 gram 1 degree C for mercury, but it takes a lot of heat for water. Now, you'll see the other units that I have in here as well. Again, this would be used in English units or imperial units. So you've got calories per gram degree C. So how many calories does it take to raise 1 gram 1 degree C? We really won't use that here in this class, but I did want you to know that it applied here as well. And then the other one here, the difference between this one and this one is that this one, the temperature is in Kelvin. Now, the good news here is that because we're dealing with changes in temperature, it does not matter what your temperature is in. You are just going to be calculating the change in temperature, and a change in degrees C is equal to a change in Kelvin. So my advice to you is whatever the temperature's in, find the change and don't try and convert units. All right. The specific heat of water, like I said, is pretty high as that 4.18 joules per gram degree C. And you will have experienced this if you've ever tried to microwave something. If you microwave like a meat like chicken, it's going to take maybe 30 seconds to heat up, and it'll be really hot. But it also cools down really, really quickly. Whereas if you're trying to heat up something that has a lot more water content, like soup, it's going to take you're going to be microwaving that for like 2 minutes at least. And it's going to hold on to that heat a bit longer. So the specific heat of water is pretty high. Now, a calorie is actually based on water, and so the specific heat of water is 1 calorie per gram degree C. But again, we won't deal with the calories here in this class, only with the joules. This is located on your reference tables. I pointed it out just a minute ago. Okay, so here is our formula. So the others did not involve a change in temperature because we're going through a phase change. So this would be if we have a temperature change and they're talking about Q. So if you see what is the heat and a temperature change, this is the equation you are going to have to use. So Q is the heat lost or gained, and it's going to be in joules. Then M is mass, so those two parts are the same. The next one, C sub P, is our specific heat, and it's going to have units of joules per gram degree C, or joules per gram Kelvin, whatever we happen to be dealing with. Now, this right here is our next variable, delta T. Delta is a Greek letter that looks like a triangle, but let's call it delta and not the little triangle. And we use it a lot in chemistry, and what we use it for is to mean change in. So if capital T is temperature, delta T is our change in temperature. Again, it can be in Celsius or it can be in Kelvin, whichever they're going to be equal to one another because we're dealing with a change in. Now, the way you are always going to find our change in temperature, so delta T is our change in temperature. It is your final temp minus your initial temp. Or final minus initial. Always. And sometimes that'll lead to a negative number, but that's okay. That's the way delta T is calculated. All right, so now let's work some problems dealing with this new equation here on calculating heat if there is a temperature change. Okay, so I have a piece of copper alloy, and it has a mass of 85 grams. It's heated from 30 to 45 degrees C, and in the process, it absorbs 523 joules of heat. What is the specific heat of this copper alloy? All right, now if it was pure copper, I could actually just look this one up on my reference tables to figure out what the specific heat is. But this one is not pure copper. It is a copper mixed with something else. So I can't use my reference tables on that. we're trying to solve for specific heat. So I like to start with rearranging my equation. So Q equals MC delta T. I'm looking for specific heat, and that's this variable right here. So to get it by itself, I'm going to divide both sides by M delta T. So this is going to be specific heat is equal to Q divided by M times delta T. All right, so now I need to find my variables. So I've got 85 grams, that's a measurement of mass. I have a 30 to 45 degrees C, that's going to be my delta T. So final temperature minus initial temperature. And so I ended up at 45. So 45 minus my initial temperature, which was 30. That's where I started. And so that gives me a difference of 15 degrees C. And then I have 523 joules of heat. Heat is Q. So this is 523 joules. Okay, so now I can plug all of these values into my equation here. Let's do it down here. So this is going to be 523 joules divided by 85 grams times 15 degrees C. That's my delta T. Now, when I plug this into my calculator, I want to be sure to put everything on the bottom in one set of parentheses there. No units cancel out, so I have to leave them all where they are. Joules is on top, and grams and degrees C are on the bottom. And that makes sense for specific heat. That's what the units should be. Then I'm going to plug this into my calculator, and I'm going to get a difference or a specific heat of 0.41 joules per gram degrees C. That is my specific heat of this particular copper alloy. Now, once we find the specific heat of a substance, we don't ever have to find that again. It is going to be constant for that substance. The only way we would have to recalculate is if we chose a different substance. So my next practice problem is for you, and we're going to be dealing with the same substance. So that means our specific heat is going to be the same. And Q equals MC delta T is our equation. How much heat will the same 85 gram sample lose if it's cooled from 45 degrees C to 25 degrees C? So in this one, we're looking for heat, which is Q. That's what we're solving for, and this is our specific heat. You can pause this video right now and try and work it out. All right, so if we're solving for Q, mass is 85 grams. My specific heat we found in the previous problem, so it's 0.41 joules per gram degrees C. And my change in temperature here is going to be final minus, delta T is final temperature minus initial temperature. So that means we've got final temperature is 25 degrees C minus my final temperature, which is, my initial temperature, which is 45 degrees C. So I end up with a delta T of negative 20 degrees C. Degree C cancels out, grams cancel out. All I'm left with are joules, and that makes sense for heat. And so it's going to be 85 times 0.41 times negative 20, and I get negative 697 joules. Now, it is negative. In chemistry and in science, and especially with thermochemistry, we tend to use signs to tell us which direction the heat is flowing. So negative means it's going to be leaving the system and we're getting rid of that heat. It's going to be lost to the surroundings. And if it's positive, that means that heat is being added. So it is completely appropriate to have a negative value for the amount of heat being lost by a system. Okay, here's another practice problem. And this one is going to be used for identification purposes. So this is very similar to the first problem we worked. We've got the temperature of a 74.7 gram sample of a metal increases from 15 degrees C to 45 degrees C when it absorbs 2010 joules of heat. What is the metal? Well, the only thing we can use in this equation right here to identify what a substance is its specific heat. So if I solve for specific heat, so Q is my heat, and that would be 2010 joules, divided by my mass, which would be 74.7 grams, times my change in temperature. So 45 minus 15 is going to give me 30 degrees C as my change. And again, put that here in one set of parentheses. None of my units cancel out, so I have to leave them right where there are. Joules on top, grams and degrees C on the bottom. And then when I do this calculation, I end up with 0.897 as my specific heat. But that doesn't answer the question. The question is, what is that metal? So I'm going to look that up on my reference sheet. And I got this number right here. So the metal is aluminum. So an easy way to figure out what a particular substance is using specific heat. So I can use my reference tables like that where I am trying to figure out what a particular metal is. Or if, let's say, I have a problem and I know that it's a particular substance, like I know that it is magnesium, and I could say magnesium undergoes, or a 74.7 gram of magnesium changes temperature from 15 to 45 degrees C. How much heat? Well, I need the specific heat of magnesium, and I can find it here. So you can either find specific heat and identify what the metal is, or if you know what the metal is, you can look up the specific heat if it's not given to you in a problem.